In this chapter, we're going to look at one-dimensional motion. As you know, motion is change in location with time, and one-dimensional motion means motion in a straight line. So one-dimensional motion is motion in a straight line. Straight line. Okay, so we're going to start this chapter by discussing motion variables. So let's look at motion variables. These are the variables we'll need to describe motion. As you know, motion is change in location or position. So the first physical quantity we're going to discuss is position. We're going to use x for horizontal motion, of course y for vertical motion. Now, position is basically a physical quantity used to specify location. Okay, this physical quantity is a quantity used to specify the location of a particle. Okay, and position requires a reference point or origin. For example, let's see, if I ask you to describe the location of this point, you have to describe it in relation to some other location. For example, you can say this much from the edge of the paper and something like that. Okay, so position requires specification of a reference point or origin. Reference point or origin. Okay, so because of that, position does not have a unique value. Its value depends on the choice of a coordinate system or of origin. Okay, we're going to have different values for position depending on where the origin is. For example, let's say if you take this points over here, okay, if I use this as my origin, then the location of this one will be 1. But if I use the location this as my origin, then this will be -1, right? So the value depends on the choice of origin. Position is not unique. Its value depends on position. And of course, the unit for position is meter. Okay, and the next physical quantity is going to be displacement. We're going to use delta x for displacement. This is simply change in position. Change in position. So mathematically, is the difference between the final position and the initial position. So you can say delta x equals the final position minus the initial position. Okay, and of course, its unit is going to be meter. Okay, now displacement is positive if the particle is moving to the right. Okay, because the final location will be bigger than the initial location, and it will be negative if the particle is displaced to the left. Okay, so delta x is positive if displaced to the right, to the right, and it's going to be negative if displaced to the left. So these are the sign conventions for displacement. Displacement to the right is positive, and displacement to the left is negative. Next, we're going to look at average velocity. Average velocity. This is defined to be displacement per a unit time. We're going to use p bar for it. So the definition of average velocity is displacement per a unit time. Per a unit time. Mathematically, we can write as average velocity equals displacement divided by change in time. Okay, or we can say delta x is final location minus initial location divided by final time minus initial time. Okay, so we can usually set our initial time to 0. So you can also write this equals x final minus x initial divided by time taken. Okay, so as you can see from this equation, the unit of velocity is the unit of displacement divided by the unit of time, which is meter per second. Okay, now let's look at the sign convention of velocity. Velocity is displacement divided by time, but time is always positive, so the sign of velocity is actually the sign of displacement. So velocity to the right is positive and velocity to the left is negative. Okay, so velocity is positive if to the right, if the motion is to the right, and it's negative if the motion is to the left. Okay, so these are the sign conventions for velocity. Velocity to the right is taken to be positive, and velocity to the left is taken to be negative. Now let's look at instantaneous acceleration. Instantaneous velocity. Instantaneous velocity, you can say, is velocity at a given instant of time. Another way of defining it is that it is average velocity evaluated at a very, very small interval of time. So let's use that definition. Instantaneous velocity is average velocity evaluated at a very, very small or infinite small interval of time. Okay, so you take average velocity, which is displacement divided by delta t. Now if you push this delta t to 0, okay, if you take a very, very small interval of time, in the language of calculus we can write it as follows. If you take the limit of this expression as delta t approaches 0, that is what we call instantaneous velocity. Okay, but if you remember your calculus, this is the definition of something. The limit of delta x by delta t, you see as delta approaches 0, this becomes dt, this becomes dx by dt, and that's derivative. So velocity is simply the derivative of position with respect to time. Okay, so instantaneous velocity is the derivative of position with respect to time. Okay, so in words we can say instantaneous velocity is the derivative of position with respect to time. Next, we're going to look at average acceleration. Average acceleration. We're going to use a bar to represent it. Okay, so average acceleration is defined to be change in velocity per unit time. This is change in velocity per a unit time. Okay, so mathematically we can write this: average acceleration is change in velocity per a unit time, or divided by the time taken. Or we can write this one as v final minus v initial, t final minus t initial. Okay, you can usually set the initial time to 0, so we can also say average acceleration equals vf minus vi divided by time taken. Okay, so let's look at the unit of acceleration. As you can see from this formula over here, it is the unit of velocity divided by the unit of time. So that is meter over second divided by second. Therefore, the unit of acceleration is meter per second squared. Now let's look at the sign convention for acceleration. Well, time is always positive, so the sign for acceleration is going to be the sign of the change in velocity. Now if the velocity is increasing, the final velocity is bigger than the initial velocity, so the acceleration will be positive. But if the velocity is decreasing, the final velocity will be less than the initial velocity, and this will be negative. So the sign convention for acceleration is that it is positive if velocity is increasing and negative if velocity is decreasing. So you can say that acceleration is positive if velocity is increasing and negative if velocity is decreasing. So this is the sign convention for acceleration. It is positive if velocity is increasing and negative if velocity is decreasing. Now let's look at instantaneous acceleration. Instantaneous acceleration. We're going to use A for this one. Okay. This is acceleration at a given instant of time. But you can also define a different way. We can say it is average acceleration evaluated at a very, very small interval of time. Okay. So let's use that definition. This is average acceleration evaluated at a very, very small interval of time. So we start with the definition of average velocity, average acceleration, which is delta v by delta t. Then we push delta t to 0, and that is written in the language of calculus as the limit of this ratio as delta t approaches by 0. Okay, that is what we call instantaneous acceleration A. Now you see, in calculus is the definition of something. It's the definition of the derivative of velocity with respect to time. So acceleration is the derivative of velocity with respect to time. Okay, acceleration is a derivative of velocity with respect to time. So in words we can say acceleration is the derivative of velocity with respect to time. Okay. Now we can also express acceleration in terms of position. We know that velocity is the derivative of position with respect to time. Okay, so we have acceleration equals the derivative of velocity with respect to time. So we have, this is a derivative of velocity, which is a derivative of position with respect to time, and this one is second derivative of position with respect to time. So in terms of position, acceleration is the second derivative of position with respect to time. Okay, so these are the motion variables that we'll need to discuss motion. Now we don't need to go beyond acceleration because our goal is to look at the relationship between force and motion, and force depends on acceleration, so we don't need to go beyond acceleration to describe what we're interested on. Okay, now we're going to look at some examples. Okay, suppose the position of a particle, suppose the position of a particle varies with time, according to the equation, let's say x as a function of time equals maybe 2t squared plus 4t maybe plus 6. That's how the position of a particle depends the position particle depends upon. Okay, so let's ask some questions. Number one, let's ask where is the particle, where is the particle, let's say after 10 seconds. Okay, so we're being asked to calculate the value of x at t equals 10. Okay, so all we're going to do is plug in t equals 10 into this equation, right? So you've got 2 times 10 squared plus 4 times 10 plus 6. Okay, and that is 246 meters. So this is the location of this particle after 10 seconds. Okay, 2, let's say calculate its displacement, let's say between t equals 3 and t equals 1. Okay, so we want to calculate displacement between t equals 1 second and t equals 3 seconds. All right, so we're looking for delta x. Okay, but we know that delta x equals final position minus initial position. Okay, so the initial position is x at t equals 1, and the final position is x at t equals 3. Okay, therefore delta x is the position at t equals 3 minus the position at t equals 1. Okay, so we go back to this equation over here, which is 2t squared plus 4t plus 6. So basically this is 2t squared plus 4t plus 6 evaluated at t equals 3 minus 2t squared plus 4t plus 6 evaluated at t equals 1. Okay, so we get the following: 2 times 3 squared plus 4 times 3 plus 6 minus 2 times 1 squared plus 4 times 1 plus 6. Okay, so you've got 9, 18 plus 12, 30, this is 36. And then this 2 plus 4, 6 plus 6 is 12. Okay, so that is 24 meters. So the particle was displaced by 24 meters between the first and the third second. And what does this positive means? It is being displaced to the right. If it was negative, it would be to the left. All right, so number 3, let's say calculate its average velocity, let's say between, let's say take the same problem, t equals 3 and t equals 1. Okay, so we're looking for average velocity. Average velocity by definition is displacement per a unit time, delta x divided by delta t, where we have x final minus x initial divided by let's say t final minus t initial. Okay, x final is x at t equals 3 and x initial is x at t equals 1, and that will be 3 minus 1. Okay, we have already calculated this over here, which is 24, so basically 24 divided by 2. Okay, we've calculated this displacement in question number 2, that's 24. So the average velocity will be 24 divided by 2, which is 12 meters per second. So average velocity equals 24 divided by 2 equals 12 meters per second. Now, number 4, let's say calculate its instantaneous velocity, let's say after 5 seconds, or it equals 5. Okay, so we want to calculate the velocity at t equals 5. That's what we want to do. But we have the expression for position, we don't have the expression for velocity. So first we have to obtain the expression for velocity, and we know that velocity is the derivative of position with respect to time. But we're told position varies as a function of time according to this equation, 2t squared plus 4t plus 6. Okay, so that'll simply be the derivative of this expression. So the derivative of this one is 4t plus 4 plus 0. Okay, so that's how the velocity changes as a function of time. And we want to calculate the velocity at t equals 5. So we just plug in 5 over here. You get 4 times 5 plus 4. That is 24 meters per second. Okay, so the instantaneous velocity after 5 seconds is 24 meters per second. All right, now let's calculate average acceleration, let's say for the first 4 seconds, let's say for the first 4 seconds, that is between t equals 0 and t equals 4. All right, so we're looking for average acceleration. By definition, average acceleration is change in velocity per unit time, or delta v divided by delta t, and that is v final minus v initial divided by t final minus t initial. Okay, so in this problem we're saying in the first 4 seconds, so our initial time is 0, our final time is 4. Okay, and v final would be the velocity at t equals 4, and v initial would be the velocity at t equals 0. Okay, so the average acceleration is the velocity at t equals 4 minus the velocity at t equals 0 divided by 4 minus 0. Okay, now remember, the velocity as a function of time is 4t plus 4. Okay, so this equals 4t plus 4 evaluated at t equals 4 minus 4t plus 4 evaluated at t equals 0 divided by 4 minus 0. 4 minus 0. So this is 4 over here. So if you put 4, you get 16 plus 4, 20. And then if you put 0, you just get 4 divided by 4. Okay, so that is 16 divided by 4, or 4 meters per second squared. Okay, now let's look at instantaneous velocity. Let's say calculate instantaneous acceleration. Calculate the instantaneous acceleration, let's say after, let's say 10 seconds. Okay, so the question is calculate acceleration at t equals 10 question mark. Okay, so we don't know how acceleration varies with time, so first we have to obtain the dependence of acceleration on time. Okay, but we know that acceleration is the derivative of velocity with respect to time. Okay, and we just concluded the the velocity as a function of time is given by 4t plus 4. Okay, so this is the derivative of 4 times time plus 4. Okay, so the derivative of this one is just 4, and because the derivative of 4 is 0. So the acceleration as a function of time is 4. So what is the acceleration at t equals 10? Okay, so we're told the acceleration does not depend on time, it's always 4, it doesn't matter what the time is. So the acceleration at t equals 10 will simply be 4 meters per second square. Now, suppose you know the velocity of a particle. Suppose the velocity of a particle varies with time according to the equation. Let's say v of t equals, let's say, 2t squared plus 3, let's say. Okay, if the particle was initially at the origin, where is it after, let's say, 2 seconds? Okay, so we know how the velocity changes with respect to time, and we're told initial the particle's origin, which means initial position is 0. We want to find where the particle is after t equals 2. Okay, so first we have to get an expression for the velocity as a function of time. Okay, now velocity is derivative of position with respect to time. Okay, but we're told that is 2t squared plus 3. Okay, so now we're going to have to integrate. So we have dx equals 2t squared plus 3. Okay, so let's integrate both sides. So this goes from 0 to t. This goes from initial position to final position. All right, so the integral of dx is x. So you've got this goes from x initial to x final, and this integral over here is 2t squared over 2, just t squared, plus 3t. Okay, evaluated between t equals 0 and going to t. Okay, so this gives us x final minus x initial, and then of course we get t squared plus 3t, and then at 0 this is 0, right? So this is the integral. That means I'm told x initial is 0, right? Therefore x final is simply t squared plus 3t as a function of time. Now we can calculate the position at t equals 2. Okay, so the position at t equals 2 equals the integral t squared plus 3t at equals t equals 2. Okay, it's got t squared plus 3t evaluated at t equals 2. All right, and that is 2 squared plus 3 times 2, which is 4 plus 6, 10. Okay, so after 2 seconds the particle is 10 meters away from the origin to the right. Okay, now number 8, let's say if the acceleration varies with time, let's say according to the equation a as a function of t as a function of time, let's say equals 4t plus 1. Okay, now if initially the particle is at x equals 2 and its initial velocity, let's say, is 4 meters per second, where is the particle let's say after 5 seconds? Okay, so the question is to find the value of x at t equals 5. Okay, so but what we have is the dependence of acceleration on time. Okay, so we have acceleration depends with time according to this equation. All right, but we know that acceleration equals derivative of velocity with respect to time. Okay, so dv by dt equals 4t plus 1. All right, so that means dv equals, let's cross multiply, times dt. All right, so let's integrate both sides. This goes from t equals 0 to t. This goes from initial speed vi to the velocity as a function of time. Okay, so the left side gives us the velocity as a function of time minus the initial speed, and that gives us the integral is 4t squared divided by 2, or 2t squared. So we have 2t squared, and then the integral of 1 is t plus t. Okay, now we're told the initial speed is 4 meters per second. Okay, according to the problem, vi is 4 meters per second. That's the initial velocity. All right, so you've got v of t minus 4 equals 2t squared plus t. That means the velocity as a function of time is 2t squared plus t plus 4. Okay, so we have the dependence of the velocity on time, but we're looking for the dependence on position on time, so we got to integrate once more. Okay, now velocity is the derivative of position with respect to time. All right, and so this equals 2t squared plus t plus 4, right? And we can cross multiply, so we've got dx equals 2t squared plus t plus 4 times dt. Okay, and then we integrate this. This goes from 0 to t. This goes from initial location to x as a function of t. Okay, so you get the integral of dx is x, so you get x of t minus xi, the initial, equals this integral, which is, this is 2 cubed over 3, so it's going to be 2 over 3 2 cubed. This is t squared over 2, and this one is 4t. Okay, and this is evaluated between 0 and t. So we have the following: x of t minus the minus the initial position equals this minus 0. Okay, so this is 2 over 3 t cubed plus t squared over 2 plus 4t. All right, and we're told the initial position of the particle, you see, the particle is at x equals 2. So that means the initial position is 2 meters. Okay, so you've got x of t equals 2 over 3 t cubed plus t squared plus 4t plus 2. That is this x initial, move it to the other side. So the question is to calculate x at t equals 5. Okay, so now we have the dependence of position on time, so we can calculate x at t equals 5. All right, and that is 2 cubed times 5 cubed plus 5 squared plus 4 times 5 plus 2. Okay, so you've got 125 times 2 is 250 over 3 plus 25 plus 20 plus 2. Okay, so that's 45 plus 2, 47. So you've got 250 over 3 plus 47. That'll be 250 plus 148 over 3. That'll be 398. About 398 over 3.